Okay, everyone, I'm happy to restart this session. So my name is Boris Merman. I'm from Stanford University, and I'm going to be the moderator. Our first speaker is Bill Chappell from DARPA. He's the director of MTO since 2014. Prior to this, he was a program manager at DARPA, and before that, he was a professor. So welcome, Bill.
Thanks. All right, so we'll take a little bit of a different tack at describing sort of machine learning at the edge. And you saw some great hardware demonstrations. I'll talk a little bit about what the government's doing in terms of sponsoring hardware development, but then also talk about why we care and some of the applications that we're looking at. So we kind of roadmap, what we're doing today or what we can do today and what we're kind of poking into in the future. There's kind of various levels of cognition. The thing that actually went really well was our N0 program, where we basically told sensors to pay attention. So really low power wake-up sensors that basically said, it's time to actually take readings and not drain your battery. As you move forward in time, we're running a challenge that asks a much more difficult question, not just waking up, but how do you learn to share or parse a shared resource, right? And then if you go to the grand finale of what we're pushing for, right, it's learning to learn. So how do you do in-field experiential learning? So we have a bunch of different programs that kind of tap in across that entire sort of spectrum of levels of difficulty, but I'm going to highlight three before we dive a little bit into the hardware that we're sponsoring. So first is the N0 program. How do you sense with no to low power? Call it N0 for near zero, and we kind of classify that as 10 nanowatts and below. So how in a 10 nanowatt class sensor are you going to have the awareness to say, pay attention? The DARPA Spectrum Collaboration Challenge is a program asking a harder question, which is how do you share information? How do you parse a shared resource, empowering the edge devices to figure out how they're going to get along? And then the lifelong learning program is how are you going to handle surprise? So how are we going to have an increased level of safety because our systems can flag that they should no longer be trusted, and with the ultimate goal then of being able to reconfigure, right, to be able to operate again. So you're going to hear later from the University of Michigan the details of their version of this program. And so I don't have to dive deep into the technology here, but I want to share kind of what the vision was of these off but alert sensors. So when we were brewing up this program, I had a young child. She's my third child, right? And after my first child, I woke up every hour thinking the miracle of life is great. I can't believe it's alive. Let me go check on it, right? By the third child, I slept pretty soundly, right? And she had to scream pretty loud for us to actually get out of bed. All right, so what we're trying to do here with N0 is third child parenting. You actually get to sleep, right, and pay attention, right, when you're needed, as opposed to, right, this wake up cycle. And that's incredibly important because if you're going to do, trillions of sensors, those trillions of sensors are not going to be generating data that matters, right, very often. If you have hundreds of sensors across the parking lot, right, only occasionally are you going to get an anomalous behavior that you actually want to flag and take a look at. You can look at our examples here, base perimeter monitoring, critical infrastructure protection, let's say bridges and or structures, forest fires, right? You hope you don't have cracked bridges. You hope you don't have forest fires on a regular basis, right? But you want to protect systems from those rare events. And if you're waking up to know if you're needed to look for rare events, you will waste all of your time in a wake up cycle. And that's why we created the N0 program. So Dennis is going to dive into actually how they get this done at such efficient levels. But they were pushing feature recognitions. They started with an SVM and then went to a CNN with about 12 nanowatts, 12 to 20 nanowatt class power draw. Now, that's difficult to do. You've got to do everything really from scratch. And our goal here was a generator versus a truck versus a car. Relatively simplistic classifications. hard to do. I can't say simplistic and then look at the PI and with a straight face. So it's really hard to do, obviously, especially at those low power levels. But all that's got to do is wake up and then say, so you can be wrong or maybe overly optimistic, right? There's an event happening, but then you turn on a bigger sensor and that's going to actually give you that refinement in more detail. So that's one way to do that, is to embed very, very small machine learning into the feature identifier in this low power class of transistors, or sorry, into these low power class of circuits. Or the other way to go, which is our RF distribution, where we're now at sort of 100 minus 105 dBm sensitivity of waking up. And this is sort of your partner nudging you, right, to wake up, right? So you're not waking up on the vent. This is someone else says, hey, I don't want to get out of bed. Your turn, right? So it's the RF version of a nudge. But now you can be aware of your RF surroundings, right, and have a keyed signal that then turns on turns on your system. So I think this is important. This is sensitivity. This is what you could buy as wake-up receivers when we started the program, all these blue dots. So this is sort of our industry analysis. And this is what we push the community to go do, phase 1, phase 2, and phase 3. There really isn't, I would say, machine learning inside of this. This is just an easy pattern matching challenge. But for 33 nanowatts, they're kind of down in this minus 100 dBm. So that's waking up from a cell phone signal. We're not using those frequency bands, but those power levels, you can now be kilometers away. Okay? So you can now distribute information in a very sort of different way. So that is our push to allow systems to wake up when they're needed, but only when they're needed, so you can actually look for sparse events. To get a little bit more complex, we walk from saying how to just pay attention to how to share information. We created a grand challenge, which is the Spectrum Collaboration Challenge. This is edge intelligence, but it's sort of in a different way of edge intelligence. A lot of people are looking at how do you look at pictures on a camera, which is a great thing to go do. We also do that. This is a little bit harder in that it's asking how do 100 or more individual edge elements figure out how to share a collaborative resource. So it's ensemble intelligence. Right? If we have the machine learning that all you guys are going to provide, right, that's great, but nothing's going to operate in isolation from each other. All of us are independently trained. We have social norms that figure out how we actually get along, right? We need that level of intelligence in our edge systems if they're going to share a resource, and the RF spectrum is a good shared resource. So, all right, so what am I showing here? So what we created is a virtual environment, which, for example, the city of Austin has been ported into a virtual environment we call the Coliseum, and we plugged in hundreds of edge nodes or radios, which had a GPU, a CPU, and an FPGA. And we then, without an FCC or any Spectrum manager, said, get high-level tasks done, right? So through that virtualization, we then can run through hundreds of scenarios, right? So you can do radio development 365 days a year, where you're just getting smarter and smarter. Think of maybe Dota 5 or what the OpenAI community is doing, but we're doing this for sort of next generation 5G or next generation wireless access. So you can run all of these different scenarios, and instead of saying all of these boxes get pre-allocated frequencies, figure out how you're going to communicate. So that edge intelligence shows itself in the fact that we don't have to do pre-planning, right? When we went to Haiti, right, the number one problem was we didn't have communication devices that interoperated. Right? When we went to 9/11, we had problems with communication devices. In theory, we can program everybody's software so it's going to figure out how to collaborate. In practice, right, life's not that simple. The ability to actually show up and interoperate because you have intelligence built in is a different way of looking at that problem. So it's easier, right, to be able to just show up, have a band that's unlicensed, but figure out how they're going to actually work together. But it's also much more efficient, right? Just like you and I have cognition, and we share the 10 kilohertz resource, which is our audio spectrum, right? We don't go around selling portions of our audio spectrum for billions of dollars like we do the RF spectrum. Even the RF spectrum is much bigger. We end up, right, having intelligence to know how and when we should talk. Sometimes Takes a little longer for the chair of the session to get people to sit down and listen, but overall we're pretty good at actually knowing how to share a common resource, and that's basically edge intelligence that allows us to do that. So for the first time in our last round, we were able to show that if this is pre-allocated FCC-like allocations, we can actually do up to 53% higher, right, by enabling those radios to figure out what the opportunity exists at any one moment. So you can kind of see what this looks like in practice. This is that virtual Coliseum. This is streets of Austin. Let's say after a hurricane, you've got first responders showing up, right? And these are different first responders which are being tasked with high-level tasks. Instead of a spectrum manager saying, this is how you actually need to interoperate, you stay over in this lane, you stay over here, right? We're saying this is the data that needs to get through. This is the voice data that gets through. We then amplify and make it harder, say these are images that need to get through, and then ultimately video, right, and everything you would expect in the technology that first responders have today. So you got UAVs, right, flying above. You then have these first responders walking through, checking for safety and whatnot. And then you see the frequency. This is time on this axis, frequency on this axis, and in microsecond time scales they're having to figure out, right, where is everybody else heading? Who do I trust? Actually, we use neural nets to figure out, right, the trust quotient of other networks, right? That none of this is pre-planned, so you don't know, are they going to do the things that they've done in the past? So it's a level of intelligence that I think we're learning. It's really hard. This is still sort of one of those things that's DARPA hard and pretty far into the future, but we've been able to show pretty good results in the first 2 years. And we're going to have our grand culmination this year at Mobile World Congress, LA, October 22nd, 24th. We've got 10 teams that'll be necked down to our first, second, and third places doing various scenarios. We did wildfires. We did this, clearing the streets of Austin. We did different coffee shops that spike in data when you have very congested, let's say, mall type of scenario. So we'll walk through those different scenarios in that virtualization space and just see how well our teams do. Things we've learned. The first year, no one used the GPU and the FPGAs, right? We provided these resources. We said it's a machine learning challenge. Let's see, we got to give everybody these specialized hardware. It turned out that, right, if you were hyper reactive and trying to figure this out sort of week by week in this challenge format, the community basically said, if I dedicated something to a GPU, it locked me in too much. I'd rather peg my CPU to 49 cores are pegged, and I was shocked. That was actually probably the biggest surprise that I had. That was the first year. The second year, I would say it's much more blended. A lot of people are using more sophisticated machine learning techniques and using some of the resources that we have. All right. So the real question is still an open question, right? Is AI going to be good for games, or is it going to be good for things that actually impact society, like how we allocate the spectrum? Still an open question. We're going to have to trust the results. One of the ways to trust results shown here, right, is a lot of people just forget flops matter. Right? Moore's law is why we actually are where we're at today, and this is from Bill Dally and NVIDIA. And even though he says Moore's law is dead, he's also saying, right, that the more flops that we've been given is the reason that we go from 16% error to 3.5% error. Now you have to do that, use those flops intelligently, like more model depth, right, or different training ops. But this is how we actually get the benefit that we've had today. So this mixture of architecture, right, with more devices, more flops, has given us sort of the faith that we can kind of ask the types of questions that we're asking today. As you look in the future, where are we going to head, right, there's a much harder question. What if we wanted to retrain all the time? What if you want to do in-field training? And this is just some data Wade Shen pulled together for me. Many of you know Wade, and he's going to be speaking tomorrow. Right, if you wanted to do that truly in the field, real time, right, you kind of go off the charts in terms of flops. So we asked a different question: how are we going to retrain in the field when things aren't predictable? And for the government, things are often not predictable, and we don't have gigantic training sets. So it'd be very important to have that level of flops. So we asked a question on the program L2M, lifelong machine learning. And here, however, did not know that had audio. Is there a way not to have audio? Probably a button here. All right, this will be loud. Okay.
However, after approximately 34 core hours of training, the self model became consistent with the physical robot to within about 4 centimeters. The self model was good enough to allow the robot to use the simple internal planner to perform a pick and place task
Okay, so what you're seeing is the result of a learned system that has an internal representation of itself, right? So now instead of asking, how do I very efficiently just do pattern matching, right? We're actually asking the system to do self-play, right? So over time, it learned how to teach itself to do this task through a reward system. Why is that important?
changes to its own morphology due to damage, wear, or adaptation. For example, here, we replaced one of the robot arms with a longer, slightly deformed part. The robot automatically detected the change and reimagined its self-model. The deformed robot could then resume its task with little degradation in performance. In this paper, we showed why there's a strong incentive for a machine to learn.
All right. What you saw there, right, is it handled surprise. It was trained under a certain level of conditions, like my arm, right, is yay big. You deform that arm, make it longer, that's surprise, but it actually was able to go back and do its original task. So you go, right, from the simple question of how do you wake up, how do you share, how do you handle surprise, and that's going to be very important as we try to use these type of resources. You can either handle surprise by saying, I'll figure it out, right? Or just saying, don't trust me anymore, right? And that's going to be a very important capability. All right, so those are some of the applications. Underneath this, we need huge hardware leaps, right? We're going to, no matter what you do at the algorithm level, you're still going to need the better processing. We kicked off the DARPA 3D SOC program as part of what we call the Electronics Resurgence Initiative, or ERI, which is $1.5 billion over the next 5 years, and the basics of electronics, and many of you are already performing on it. 3D SOC is looking at what Stanford had done under some previous funding, which is take 90 nanometer base level silicon and grow low temperature materials like carbon nanotubes and ReRAM vertically. So now I've got processing, memory, processing, and memory now truly co-mingled, right? Within submicron distances, you now have the memory and the processing together. Frank, I actually can't do a better job than Naveen just did, right? So we're looking at deep in-memory architectures, very much along what he said, though we are doing probably more at the device level. How do you optimize the materials that would allow you to have those types of benefits? You can use SRAM. I know companies are already starting to do that. We're looking at new materials that would even make that even better. And SDH then is asking a question, right, of, there's a really interesting tension that was brought up. I think it's great to co-optimize from the hardware through the software. You architecturally will get huge benefits. How often are you going to be able to do fresh hardware design in time for your result? I think it's an open question. So we have a lot of work trying to lower the barrier to design and manufacturing. But the alternative here is software-defined hardware, right, where you reconfigure coarse-grained, reconfigurable architectures based on the data that you're sensing, based on whether it's sparse, right, or whether it's dense. It becomes the chip architecture you want in real time. So there's some of the hardware plays that we're looking to kind of help this next generation of systems. I think for time, I'll leave it there. I've got details on each one of these programs, but come find me if you're interested on any of those.
Thank you very much, Bill. We have time for 1 or 2 questions.
Question?
Yeah, Bill, thanks for the fascinating presentation. For the first category of sensors, tiny near zero sensors, I thought the challenge will be more on the communication side. How do you get to nanowatts to get these sensors onto internet. What are your thoughts there?
So that's a great point, and it shows you what we're not doing, right? We're basically waking up a system in these sparse events. You wake up a milliwatt class system. You could wake up a watt class system, right? If you're only waking up on demand. So we can still have high power transmitter, but you can't send, erroneous data or false data, right? So that classification of when to kick on the bigger system is the hard part in what we're doing. We aren't tackling the rest of the problem. The rest of the problem is basically COTS. But you take COTS that operate for, let's say, one system we are now deploying is something like 7 to 8 days worth of operation in the field. It is multiple years, right? And that's a function of the sparsity of what you're actually looking for, obviously. But if you were to look for a rare event like a road that is very rarely traveled on, you can now deploy that system for multiple years at a time, even though it has a watt transmitter.
So I like the concept of the sensor that only wakes up when something does happen. What about a scenario where you want to be sure that nothing did happen, where you actually want those zeros to be assured that we know nobody entered this area over time?
Yep. So there's multiple scenarios. We were looking at sparse events. If you have a continual event, you need to do all the things that everyone else is already describing, is drive your continual operation down past the milliwatt class. We're working with ARM, for example, in some of their sub-threshold processors, right? So that those would be continually operating sub-milliwatt class. More traditional, I'd say, research, even though it's really hard because it's sub-threshold. But anyway, so there's specific class that we're looking at, and then you just have to drive the entire compute stack down if you're going to continually monitor.
Okay, thanks again, Bill.